The next one, number 6, has actually already been solved. It asks us to show that the two topologies on the spaces RL and RK are not comparable. RL is the set of all real numbers with the lower limit topology, and RK is the set of all real numbers with the K topology. We have already shown that they are not comparable, so that means there is no need to solve this. Next we see number 8. This is the last one of this section. It has two parts. This is part A. In part A, we have to apply lemma 13(2) to show that this countable collection forms a basis for the standard topology on R. What is this collection? It consists of all open intervals a, b, where a is less than b and a and b are rational numbers. That is why it is countable. So we start the solution to part A by noting that the elements of this collection are all open in R, and here open in R means in the standard topology on R. That is because these are ordinary open intervals where A is less than B. So that is the first condition that a collection must satisfy in order to be a basis for an already existing topology on the space. Alright, so next what should we see? We take any open set U in R, again open with respect to the standard topology on R, and any point x in U. Then by the definition of open sets, there exists a basis element in the standard topology that will contain that point and will itself be contained in the open set U. And the basis elements in the standard topology are ordinary open intervals. So that is why I wrote, for these things there exist two real numbers a and b satisfying this inequality a less than b, such that the basis element a, b contains the point x and is itself contained in U. Note that this may not belong to this collection, because here a and b are not just two real numbers where a is less than b, but they are rational as well. So next we choose a rational number R1 in this open interval a, x, and a rational number R2 in the open interval x, b. So you can see that I have intersected these intervals with the set of rational numbers. The question is, how do we know that these rational numbers exist? And the answer, of course, is the property of real numbers, that between any two real numbers there is at least one rational number. To better understand what's going on, you can look at this small figure. So this is our real line on which we have the open set U somewhere. I mean, it's some type of set, and x is a point in U. Okay. And what we found just now is that there exists an open interval a, b, which contains x inside of it and which is itself entirely contained inside U, whatever the set U is. So then you see that there is a little room between a and x. Actually, because x belongs to a, b, obviously x is greater than a and less than b, so there will be room between x and a and also between x and b. So these rooms will have rational numbers. So we have chosen one rational R1 here and another one R2 here. Then you can clearly see that R1 is obviously less than R2. Why? Because you can actually go quite logically. If you want to get these conclusions logically, you can also choose to not rely on this figure. You can see at these conditions themselves. R1 belongs to a, x means what? It means in particular that R1 is less than x. R2 belongs to x, b means x is less than R2. So R1 is less than x and x is less than R2 means R1 is less than R2. So this is a legitimate open interval in R. And what more is true about this open interval, that its boundary points, its endpoints are rational numbers, and that is why it belongs to our collection B. And you can see from the figure, or you can prove, I mean it's not a very difficult proof rigorously, that x belongs to this open interval R1, R2, and R1, R2 you can see here in the figure, the open interval whose left boundary point is R1 and right boundary point is R2 is itself contained inside a comma b, which is already contained in U. So that's how we find that for any open set U which is open in the existing topology and any point x in it, there exists a set in our collection which contains that point and which is itself contained in that open set. So this is the condition that we need for the collection D to be a basis for the existing topology, and that comes from our lemma 13.2. So that's how we get our solution to part A. And next we have part B, but before we see what part B asks us to do, let us note that in part A we have shown that the space of real numbers with the standard topology has a countable basis. Spaces which satisfy this condition are special, and we will learn more about them when we study separation axioms. However, if we try to do a similar thing to the set of real numbers with the lower limit topology, if we consider that space, then we do not get such a basis, and that is what this part B is about. Now you look at this collection, where the type of intervals we are considering is like what we consider in lower limit topology, right? You remember the basis that we use to define lower limit topology, that has intervals like this, closed, open. There, however, the boundary points of the intervals are any real numbers where a is less than b, a comma b. But in this collection, they are additionally rational, like the collection B in part A. This is also a basis for some topology on R, but that is not the lower limit topology. It is something different from the lower limit topology. That's what we have to show in part B. So we start the solution to part B with this remark. It's easy to show that the collection C is the basis for some topology on R. That means this part is left to U. And next we consider this basis element of the lower limit topology on R. This closed open interval square root of 2, 2. Note that since the left boundary point is an irrational number, so this is not in the collection C. And there exists no interval in C, no element B in C of that form, closed A, open B, where A and B are rational and A is less than B, which contains square root of 2 and which is itself contained in this. What is the reason for that? Well, that is because if you just think of it, what is B? B is an interval of the type closed A, open B. If that interval has to contain this square root of 2, obviously that interval must have its left end either here itself or on that side. But the left end of B cannot be square root of 2 because it is irrational. So it has to be on that side. But if it is on that side, then B cannot be contained in this. That is why the topology generated by this collection C cannot be finer than the lower limit topology because of this thing. Otherwise it would have been finer because we already know that result, which lets us decide which topology is finer, which one is coarser, using their basis. So if the topology generated by C cannot be finer than the lower limit topology, how can it be equal? Because if two topologies are equal, then each one is finer than the other. We are not talking about being strictly finer, just simply finer. So that is why the two topologies are not comparable. Let's write the last lines. Just now I said that the two topologies are not comparable. right? That was a slip of tongue. I meant to say not equal. So the topology generated by the collection C is not finer than the lower limit topology on R, and that is why they are not equal. They are different topologies. And with this section ends. So in the next topology video, we can start the next section, which, if I am remembering correctly, it is about order topology or maybe subspace topology. I can't remember it. So we will see what it is. So see you in the next topology video with those new things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.